All right, so I hope you guys had a good experience with the test. And if you have, once I return the test, if you have any questions about any particular questions, or if you want to go over your test or discuss it, you can come to my office hours. I'll be happy to help you with that. Now we're going to continue with chapter 7. We have two more sections left of chapter 7. There's 7, which is approximation method. That's your trapezoidal rule and Simpson's rule and midpoint rule. And then 7, 8, which is improper integrals. And that will be the one that we deal with, remove yet another condition from our functions that don't have to be over a closed interval. They can actually be over an infinite interval. Or you could have discontinuities. So that's what improper integral would be. We'll get to that. But let's talk about the approximation method. And I tell students usually that all the things we learned in chapter 7, all the techniques of integration that we learned, basically they all amount to what's in the back of the book, the table of integrals. And that's not every function. That's not every integral can be calculated like that. Some of our most common integrals that we need, like Gaussian distribution, your normal bell curve distribution, the integrand doesn't have an antiderivative, which means you cannot evaluate it using fundamental theorem calculus. So the methods we are learning, or we have learned in chapter 7, can only go so far. We need to discuss what do we do when we cannot find an antiderivative and we cannot apply fundamental theorem calculus, or maybe we can, it's just too hard and the process would be too tedious or cumbersome to do that. So what we do is we use approximation method. And approximation methods a lot of them are very natural. Like you're like, well, that's what I would have think of doing. Like, let me show you guys the first one, the first approximation method that we propose. And that's, again, assume that I partition my interval into, say, in this case, 4 partitions. So this is x0, x1, x2, x3, and x4. And I want to, of course, calculate the area below the curve. Now, before this discussion, we used to do the left endpoint. We use the left endpoint calculation for the height, or we do the right endpoint. And of course, midpoint was another option for calculating. But in this method, the method of approximation, we actually do what we're doing here. Like you straighten up, not as a horizontal line, but you do it as a point that connect, or the lines that connect the points of the curve at each partition. And then if this is area 1, and this is area 2, if this is area 3, if this is area 4. Area 1 is actually just a trapezoid. And let me just put it on the side of it. It looks something like this. That's area 1. The width of it, or the height of it, is delta x. One of the bases, the small base, is f of x0. The other base is f of x1. That's the height that we have. And the area of a trapezoid is 1/2 sum of the bases, f of x0 plus f of x1, times delta x. So if I want to calculate for 2, then I get 1/2 now f of x1 plus f of x2 delta x. For 3, I have 1/2 f of x2, one base, f of x3 is the second base, delta x. And then for 4, 1/2 f of x3 plus f of x4 delta x. If I add them all up together, I get 1/2 f of x0. And then I have f of x1 and f of x1, so 2f of x1. Once again, 2f of x2 2f of x3 plus f of x4. That's an approximation area using trapezoidal rule. So the process or whatever. So in general, if you have a partition of size n, you would say A if partition of size n, A is equal to approximately 1/2 f of the first one, and then twice of everything after. And then the last one is by itself. So that's how you calculate approximate using trapezoidal rule. In a way, if you think about this, it's really just averaging out left endpoint and right endpoint calculation. So it's the average of the two. Has a higher chance of course, being closer to the result. Okay. Now, if I want to use trapezoidal rule to calculate the area below a curve, say suppose I have integral from 0 to 2 of x squared plus 1 dx, and I want to approximate it using n equal to 4 partition. And I want to use, trapezoidal rule. Then I'm going to say, well, if n is equal to 4 and I go from 0 to 2, then it's going to be 0.51, 1.52. That's the 4 partitions. So this integral is going to be approximately 1/2 f of x naught, 2 f of x1, 2 f of x2, 2 f of x3, and f of x4. Now f of 0 is 0 squared plus 1, 0.5 squared plus 1, 1 squared plus 1, 1.5 squared plus 1, and it's just a matter of calculation. 0.25 plus 1.25, 2.5. 2.25, 3.25 times 2. One, 10, 18, 19. Now, if I exactly calculate this, six 14. Now, if I use my calculator, third is approximately 4.667. And here, I think I forgot delta x. So this times 1.5 times 1/2 times 1/2, which is 19/4. And 19/4 is 4.75. So very, very close answers. This is the approximation. This is the exact one. So very, I mean, it's still an approximation because of the decimal points, but at least we use antiderivative to calculate. So that's the, sorry. Trapezoid rule. Now, another method of approximating is what we refer to as the Simpson's rule. Now, Simpson's rule is a little bit more involved, but the good thing about it is the end result is better. The approximation is much better. So, and we'll talk about the error bounds or approximations as well, but right now we're just trying to understand the different methods. So the Simpson's rule it relies on the very simple idea that says, well, you know how you have points that are part of your graph, and you approximated them, you approximate areas by connecting the dots, and you got like straight lines. Again, this is part of a bigger picture, but Simpson's rule said, well, why do we use straight lines to connect these? Why don't we use a parabola to connect these? A parabola here, if there's two of them here, a parabola here. Not the same parabola, obviously, you can have different parabolas, but it's going to be the area under the parabola and not under two straight lines. So that's what Simpson's rule says. It says, well, why don't we do that? But the problem here is, well, how do we come up with the formula for it? So the way we prove this is by first looking at a very special case and recognizing that this is, even though this is a special case, this could be generalized to what we have here. And that is if I consider a parabolic shape above these 2 points. And I want to find the equation of that parabola that goes through 3 points. That's negative h, 0, and h. And of course, the equation of the parabola is going to be y equal to ax squared plus bx plus c. So this is going to be y0 for y1, this is y2, this is y3 as your height values. So if I plug in, I get y1 is equal to a negative h squared plus b negative h plus c. Y2 is equal to c. Y3 with the same logic as before becomes ah squared plus bh plus c. Now, if I put this in a very nice combination of, if I add y1 plus 4y2 plus y3, I end up with y1 plus 4y3 y2 plus y3 is 2ah squared. These two cancel out. these two plus c, which is going to be 6c. So have that in mind. Okay, have that in mind. On the other hand, what happens if I integrate ax squared plus bx plus c from negative h to h? Because it's a semantic interval, all functions will give you 0 when you integrate. So I'm going to have, and the rest is even, so I can do twice of 0 to h ax squared plus c. Which is going to be twice of 1/3 ax cubed plus cx from 0 to h. So you get 2/3 ax cubed, which in this case is going to be ah cubed, minus a times 0, which is nothing, plus 2c h minus 0, which is h. Notice they're the same if I multiply it by another h. If I multiply this by another h and divide it by 3, I get the same thing. So if I multiply by h, I get h cubed and h. Divided by 3, I get 2/3 and 6/3, which is 2. So the integral of negative to h of this polynomial is really this expression times h over 3. So the integral from negative h to h of ax squared plus bx plus c is h3 times y1 plus 4y2 plus y3. Now come back to the bigger picture. We come back to the bigger picture. If I have many of these, I can put any 3 of them together. Each of them is going to be a parabola. If this is x0, this is x1, this is x2, this is x3, this is x4. This one is the first 3 are going to give you the first area, and these are going to give you the second area, and more, so on and so forth. For the first area, what you're going to end up having is h, which now h is delta x over 3, f of x0 plus 4 f of x1 plus f of x2. For second area is going to be delta x over 3, f of x2 plus 4 f of x3 plus f of x4. As you would imagine, if I keep doing the pattern like the third one, if there's again, the third parabola would give you delta x over 3, f of x4, 4 f of x5, f of x6, and so on and so forth. Now, if I add these, I get delta x over 3, that part doesn't change. I have f of x0, 4 f of x1, 2 f of x2, 4 f of x3, 2 f of x4, you get the idea, 4 f of x5, right before you get to f of x6. So it is 4, 2, 4, 2, 4, 2, 4, and then there. The only important, one of the important things about Simpson rule though is, notice I could have a partition of size 2, I could have a partition of size 4, or 6 or 8, but the size of the partition n has to be even for Simpson's rule to work. Okay, that's something you have to have in mind when you're trying to solve this particular thing. Now let's use Simpson's rule to calculate the same thing that we did earlier. So I'm going to use it, but now I'm going to, n is 4, so I'm okay. I can use it for this one. I'm going to calculate this using Simpson's rule. So I have integral from 0 to 2 of x squared plus 1 dx. So n is equal to 4, no problem. So it's going to be delta x. Delta x is 2 minus 0 over 4, which is 1/2. So you're going to have an integral, in this case, integral delta x over 3, f of x naught, which is 0, 4 f of x1, x1 is 0.5, so 0.5 squared plus 1, 2 f of x2, x2 is 1, 4 f of x3, again f of x3 would be 1.5 in here. And f of x4, which is the last one, which is 2. So it's going to be 1/6, 1 plus, this is 2.25, 1.25, sorry, times 4, which is going to be 5, 8, 4, sorry, 2.25 again, plus 1 is 3.25 times 4 is 13. So I'm going to end up with 18, 22, 28. And I get 14, which is actually very close to, actually, it is the same thing as a trapezoidal approximation. Not a requirement, but it just happened to be the same. And that's your Simpson's rule. So trapezoidal rule and Simpson's rule are ways of approximating an integral. And Simpson's rule, as I will show you guys in my next video, has a better approximation than trapezoidal rule has. In my next video, I'm going to go ahead and go through this, both of them again with a different example. And I will also talk about error bounds for these, maybe in the context of the example as well. So I hope you guys are, this is helpful enough to get you through some of the problems, and then we're going to answer some homework questions and talk about the error bounds in the next video. Thank you.